It should be recording. Let's check. Yeah. Alright, another draft physics video presentation and such. So, this video was posted to me as something worthy of replying to, and I suppose it is, because it has all the jargon in it, and I can attempt to put it in the reasonable context, because it's basically just propaganda, it's distortion, so grains of truth, but that's all there are, and they've just rearranged them to suit their chosen religion. And it's just sort of made obvious by these kinds of presentations of reality.
Guys, I'm super excited to tell you that this video is a collaboration with the History Guy channel. So while this video is about Maxwell's equations, they have simultaneously uploaded a fascinating video on the interesting life of James Clerk Maxwell. Check out their video at the link in the description.
I'm sure it's a pile of shit too. This history is, who writes it?
Think of any high-tech appliance you routinely use. Your phone, your TV, your computer, your refrigerator, toaster, light bulb, your car. Just about anything. And I can guarantee...
he can guarantee... yeah, he guarantees it.
...that some engineer, somewhere, sometime, used one of these equations to design it.
Alright, just a pile of crap. Frankly, this whole argument that all of this stuff is essential, we have this quantum mechanic view, or this wave view of the universe, is something that's required to understand that there's relationships between a chainsaw and how effectively it cuts down trees based on how sharp its little blades are or something. And somehow you need an equation, or you can't figure out how to use a chainsaw. It's just such an exaggeration that we're completely dependent on Maxwell. If Maxwell didn't show up, nothing would have happened. The truth is, Maxwell showed up and nothing really happened. For like decades, nothing was done with these equations, okay? They weren't able to apply them because they still hadn't really understood the concept. I mean, when Edison invented the generator, it was a piece of crap. It was based on a telegraph. I mean, the motor was just doing back and forth. They hadn't even figured out how to maximize the function of it by making it circular. So I mean, they were so far from really understanding the connection between magnetism and electricity. These equations didn't just make it all obvious and so easy and blah blah blah. So this is, the history speaks for itself if you are accurate to it, in the sense that Maxwell didn't revolutionize the world. Okay, now, there's definitely utility for some applications, but most of this is theoretical physics. Most of these equations are used by theoreticians to, play games with reality, and, they derive these equations in specific ways where they replace functions because they find some kind of equity, just like they did with the concept of frequency and turning it into an energy function, because that's the way it works with photons. And now all of a sudden it works with everything in the universe. It's those kinds of connections that the theoreticians are using to make arguments, but they're arguments that they don't prove with real evidence.
Almost all modern technology is based on them.
Yeah, bullshit.
These are...
you people know the history. The history is people like Edison, okay? You just kept trying different things, okay? He didn't have some theory of light bulb, beyond the fact that, yes, electricity can burn stuff, and if I do it the right way, I can make it burn longer. And that's all it was. And, these equations didn't help him at all.
Called Maxwell's equations in honor of Scottish physicist James Clerk Maxwell, who published them in 1865. He's not as well known.
Right, so just think about 1865. Think about how nothing really happened until about 1900, right? Nothing really happened. The Industrial Revolution, the whole thing, it didn't just take off with Maxwell and they were on their way. It took a long time to turn any of this stuff into a useful electric motor. A long time. 100 years from Faraday really is, it took a long time to take what Faraday discovered and turn it into something practical.
as Newton or Einstein, but his contributions to science are arguably among the greatest. Somewhat like Einstein.
I mean, you know, this is again just kind of an obvious exaggeration if you know anything about it. I mean, it's nice that he took some math and he made it a little more efficient. But clearly, I mean, he's going to even point out it's Ampere's law, it's Gauss's law, it's, you know, these are the people who did it. You know, even Hertz later. And it wasn't like any of this was a mystery. That's the other thing. They make it sound like he discovered something. No, he didn't discover anything that they weren't already talking about. People were already talking about it. It's like the example of Darwin and evolution. Darwin didn't just show up and come up, hey, I have a great idea, evolution. No, people already believed it. What they didn't have was a method, an understanding of how nature does it. And so Darwin provided a reasonable explanation for how it happens. Natural selection. Blah, blah.
He built on the concepts originated by other scientists, but synthesized them and put them in mathematical terms that allowed us to see a new kind of relationship.
Right, and I would argue that the relationship you're seeing is wrong. That's probably why it took an extra 100 years to get from Faraday, because Faraday screwed it up a little. Just like Benjamin Franklin getting plus and minus wrong, Faraday talking about lines of force rather than, field lines rather than lines of force is where things started going sideways. And I'll explain.
In this case, between electricity and magnetism and light, he showed that they were really just manifestations of the same phenomena.
They really aren't. They're completely different things. I mean, they have a describable difference. It's like saying, well, elephants and people are the same thing because, they have a brain and a butt and, balls and whatever, so they're the same. Now, they're not the same thing. All right, so here he has the example of the charge. And again, that's where it starts. And it starts with Gauss. And this very simple concept that you have a charge, Q, and the charge can be understood to radiate force. That is, it has an effect that is distance dependent. And you can tell how strong the charge is by measuring it at any distance, and then understanding that the number of these lines that will intersect you will dictate how much charge you'll feel at a location. And then you can just calculate the distance and know what the charge actually is. Just like you can test how bright a light bulb is by me taking a meter here and the bulb 10 feet away, and I can count how many photons I'm collecting at this distance, and I can just calculate it pretty clearly that if I get 10 here, then the bulb is producing 1,000 at 10 feet. Some kind of simple relationship that exists. And so it's a very obvious and mechanical function. And so this is how they actually do the math. So when you see the formula is really saying make 10 arbitrary lines. And your 10 arbitrary lines at this point equals 100 watts or something. 100, well, let's say whatever, 600 lumens of light would be coming out of it. So it's a charge, it's whatever the elements of charge is. And, Gaussians or whatever the fuck it is. And that they'll just assign. So you know that these lines, this number right here, this equals a certain amount of charge. And you know that at equidistant, all the way around the charge, there's another line here that's 1/2 of that charge. And then there's this line out here that's, 1/4 of that charge. And that's all. So you don't need to draw these lines. You just need to draw these lines, count them, and you could just mechanically answer your question. You don't need to do any math. All you need to do is do proportions. And so if the proportional distance. So just draw a picture of it, just like you could draw a map. I could give you instructions on how to get somewhere by giving you latitudes and longitudes and blah, blah, blah. Or I could just draw you a picture and just say, go this 1 mile this way, and then you turn left, and you go 6 miles that way, and then you turn right, and you go 5 miles that way. I don't need to give you an equation that tells you what this distance is. I don't need to do all this other stuff. I can just give you the map that'll tell you the answer. So they already had this. This is what already existed as a way of understanding. So just understand that's where it starts. Those are lines of force, and they're used, and they were used as a way of representing charge that functions just like light. So again, it has another feature that's connected to light. Without even talking about speed, we already know it has a feature just like a light bulb. See, they didn't have light bulbs, but they had candles, they had other sources of light that were basically even in terms of their distribution. And so this concept was already known. We already had the sun, for example. So we knew the amount of light that's lumens, the number of photons hitting the Earth changes as you move the Earth further away and closer to the sun. And it changes by the R squared, which is basically a rule created by the fact that light diverges in 2 dimensions. And it makes a square when you have 2 dimensions. And it's that area that is the inverse square law. And that's why it obeys it. So no waves involved. See, I mean, Maxwell was a wave guy. He believed in an ether. And that's why they glorify this crap, is because they believe in an ether. They won't call it that, but that's what they believe in. They believe there's some magic thing called the field of magical stuff that somehow is got all kinds of waves in it caused by everything's waving it. When obviously, I would argue what can be deduced from a light bulb is that there are elements coming off the light bulb, and the elements travel a distance, and there's more of them the closer I get, I'll hit, than the further away I am, and it's that simple.
This is one of the most important and practical set of ideas in all of classical physics.
So this is this is the big mistake. See, they just took those lines and they bent them. Now those are lines of force. So that's what another charge will do. So if I put 2 charges in the environment and they're both just radiating, okay, that's all they're doing. They're just radiating. And if I put 2 opposite charges, this in pink, you could understand that there'll be places where these lines intersect. And all the field lines is a recognition of the dilution. So you have, this is like a 10, this line, when they intersect, they're going to intersect at different strengths, right? So this one's going to have so much energy this way because it's a much shorter line, and this is going to be less of this. And so I can mathematically understand that if I add this much pink to this much white, okay, then I'm going to get an end result that'll be, some lesser amount of pinkness, some shorter line that'll be the amount of force that's actually going to exist at that location. And the solar light went out. I have to turn that on, I suppose. Yeah. It's not on. I think I turned it on, so I think I've run out of solar energy. Yeah. Maybe it wasn't on. Maybe. Yeah, it looks that way. All right, anyway, where was I? So yes, so then you can understand that the curved line is just a representation of the dilution of the force. The fact that you're always going to, it comes out straight and then it dilutes by how much of this you're exposed to. So it's really, you're just saying, what's the mixture of white and pink, and where would something line up in that mixture, whether it was a negative charge or a positive charge. And that's all these lines are. So these lines are arbitrary. The real lines are these straight lines. They're the real lines, and if you can use those, okay, there's no rule or law against it. And so if you use the straight lines, you can do exactly the same mathematics.
Even Maxwell could not have imagined their huge implications for technology.
Oh, whatever. They're telling you can't imagine a sofa. who knows what he could imagine. So even that's just saying, what they can't think about miniaturization, and they can't think about, possibilities, and I'm sure they could.
Not only do they describe about
novels were written, about the future back then, and they had lots of ideas. It's not like, nobody ever thought of having some kind of it is kind of lame when you think of like Star Trek and stuff, just because they have a view screen that goes boing, that makes noises, and they have communicators that you have to press the button. It is kind of funny.
Every electrical and magnetic phenomenon, but believe it or not, hidden within these equations is a fundamental truth.
See, that's what they're after. They're after this idea that these equations somehow demonstrate that their, wooey theory of wobbly bullshit is somehow the truth, when no, it's a mechanical straight line universe. It isn't doing any of this wooey, wavy crap. Waves are emergent properties. It's what, it's I can use the bullet analogy. I can use the soldier analogy. You can create waves with discrete objects, but they are not elemental. They're something that emerges out of making a lot of something.
About the nature of light and why it is the ultimate speed of the universe. And
why it's the ultimate speed of the universe. Maxwell has no posings on any of that. It's just the way it is. Yes, light goes a certain speed to cover distance. So what? It's not instantaneous. The universe isn't instantaneously happening because something in the universe is going slower than instantaneous. So therefore, anything dependent on that thing is going to go slower, even slower. So yes, all you can do is have degrees of slowness based on how much of this speed of light crap you can trap. Make it go slower by not allowing it to get where it's going.
This truth helps set the stage for another famous physicist who would later change our paradigm about the nature of...
Yeah, he did it to you, okay? You bought the crapola, the crap answer of the bent nothing, makes things move, blah, blah, blah. Just eliminate the whole idea of having anything called a force. Force it to do something.
Reality itself. The explanation is coming up right now.
So all that crap before it even gets to the subject. Great. Full of yourself much?
These equations look intimidating, but don't worry, we're not going to derive them.
Yeah, don't worry, we're not going to explain them. So, yes, they don't look very intimidating, frankly. They just look like, okay, whatever that stuff is, it seems like all you have to do is divide that into that and multiply that times that and you're done. When that's not what it's saying. So, the dot thing doesn't mean multiply. It's a dot product bullshit. And so... those equations mean you have to put a whole bunch of other equations in the equation. So those little bits in there aren't really things. They're things that you have to expand on.
I'm only going to show you what they mean and what they imply.
So at least he's pointing out, okay, Gauss's law for magnetism, Faraday's law, Ampere's law. So again, they're already the work of somebody else, and all they are is a new configuration of the same crap that somebody else discovered. So it's just a way of saying, look, Faraday might have, well, I won't use that as an example because he did it wrong. But yes, Gauss had this concept of these straight lines. And so instead of the straight lines, we're just going to convert it into a wave. And so we're just going to see it as these points here, right? Even though we know straight lines are creating these lines. You wouldn't have these lines without the original force. So it's almost like just looking at the Earth's orbit and saying the force is this way around the Earth, when logically you can understand that no, it's a combination of two active forces. One that wants to just go out and one that's pushing it in. And so yeah, you can think of it this way. You can think of it as being these circles that are, you can think of a light bulb as creating lines around it, fields of bubble. You can do that, but it's not what the light bulb is doing.
practical terms, and we're going to visualize them with graphics that I hope you'll find useful. Objects have something called a
Yes, what the propagandists like to use is graphics, yes.
charge. This is a property of matter.
So here we go. This is the nature of the truth. So this he has correct. This is what the thing does, and it's what the math is based on, is that creates the inverse square law. That is the function. That's the elemental function. Rays of energy, of change, of something that will affect something if the ray hits it. That's the correct description. And then everything else they say is crap.
Mass is a property of matter. In practical terms, what this means for large objects with negative charge is that it has more electrons than protons.
So this is, again, you don't need to go there. I mean, all you need to know is that the electrons and protons are in different configurations, and depending on how you configure them, okay, their net charge in any one direction will be different. So depending on how I put plus and minus together, a red light and a blue light, depending on how close they are, I'm going to get different effects. You know, if I put them right on top of each other, I'm going to get a lot of purple.
First thing I want you to visualize is that if you have a static object with a charge, it will affect only other charges.
Right, so none of the field lines that actually come off the object do any of this bending. None of the lines of force ever bend. They don't do that. So it's just their way of converting from one type of map to another type of map, and that's like a fundamental error, is to take the mechanism and distort the mechanism. So, for example, like with magnetism, you could just think of it as, you know, north side and south side. Well, north side should be the negative side, and another positive being right on top of each other. So I've created a dipole, and if you thought of the dipole as just being these charges, let's just use wavy lines versus straight lines. So the positive side is producing these wavy lines, and then the north side is producing the straight lines. And you can just understand that the forces will mix here and be diluted by that process. They can't have the same effect. But if I put an electron here, it's going to decidedly go in one direction. If I put a proton here, it's going to decidedly move away, because it's not getting any shared, it's not seeing any of the red light up here, and it's not seeing any of the blue light down here. But the more it gets mixed, then the more the equidistant line isn't going to be the same force. So when you're the same distance here, or you're the same distance here, no longer will it have the same effect, because the proton put here is going to feel the attraction, the repulsion from this positive end, right? And it's going to feel the attraction to this end. So it's going to have a mixture of forces, and so it's not going to be a perfect circle around this anymore as being the same distance equals the same effect, because the two forces are now bleeding into each other. So you can get the same exact answer to any question you ask. If you want to ask a question about what's the magnetic field here, you can answer the question by just turning them both into charges, giving them both the opposite effect, that is, one's pulling towards, one's pushing away, and you'll get the same exact field line, okay, that now, instead of being a perfect circle, is now going to be this shape, because the force will be stronger here and it will be weaker here in terms of how much it's going to affect something. And now, if you want to do the dipole thing, then you put a magnet in here, and you know what the magnet's going to do. It's going to flip to match the polarity of the, to be exactly opposite the polarity of the magnet it's associated with, and the same. But you can do it with these lines. So you can use Gauss's law, you can use Gauss's equations, and get the right answer. So there's no need to do this this bending thing, okay, and force any of these lines to start here and end here. You can do that, and it will work to put these fake lines in, but you can just stick with the original lines and you'll get the right answer.
And if you have a static magnet, it will affect only other magnets. It will not affect charges. But
okay, so he just said something that's just wrong. Okay, it's just wrong. They trap charges all the time using magnets. They make the charge static. They freeze it in a position by putting charge on it. Okay, creating a field that will cause it not to move. So it's just wrong to say that.
if you have a moving charge, it will affect a magnet. And if you have a moving magnet, it will affect a charge.
Right. It's obviously going to make a difference if you keep changing something. So again, I'll just make the simple argument. You put something in the universe. Everything else is now changed. I'm getting hit by more photons because the light can reflect off the little piece of chalk and bounce and hit me. So my world changes because something's in my world. But the truth is I will adapt to that change rather quickly, okay? Just like all of these electrons and protons. If I put an extra little proton in over here, right? I put a new thing in the environment. The new thing is going to be affected by, and it's going to affect the other things, but they'll all adapt to the condition, and all the positives will try to stay away from each other, and all the negatives will try to stay away from each other, and they'll balance to the condition, and they'll just balance to the new condition. So injecting the charge will create change. That change can cause a little bit of electricity to happen in a conductor when you pop it in. And then if I jiggle it or I move it around, then obviously I'm going to keep changing the environment. Now this thing's going to do everything else has to rearrange, and you might get a little more current because you're moving the damn thing. But there's no surprise that there's a connection between moving and creating change, and change being the thing that creates the electricity. And that's all you're doing. But introducing it also created change. It's just that if you don't change it anymore, you can't create any more change, and therefore nothing's going to change in terms of your electricity. So it's just change. It's not movement, it's change. I mean, obviously change is movement, but I'm just saying introducing the charge will have the same exact effect. You can't put it into the environment without changing the environment. And all you're saying is yes, everything adapts to the change. Everything is affected, and then whatever like if I made the sun twice as hot, it would change the surface of the earth, and then the surface would be adapted to this new amount of energy. The temperature would increase, and then it would stop increasing, and everything would just stabilize again. That's not too hard to figure out. And we just know that electricity has to be caused by creating a condition, like, I've explained it before. The subtlety of electricity is that sometimes the change you're making, okay, you have to allow the change to unchange to make the change again. So if you're making, say you're exposing an atom to a field, and the atom changes shape subtly, you can sort of understand that as long as I keep the same force hitting it, it's going to stay this shape. And if I don't allow it to go back to this shape, it can't get changed back into this shape again. So you can sort of understand that there would be a point where you need to allow the pressure to go out. So you could argue that in a conductor, you could push the electrons, introduce a charge or a magnet. You could push the electrons, all right, and create a pressure. But if you don't allow the pressure to go anywhere, that is the X, whoops, I keep draw minus there. If you don't allow it to go anywhere, then it just stays that way. It can't go anywhere. But if I take the charge away and allow the electrons to relax, and then I put the electron back in and push them again, you get the idea. I can keep moving them then, and I can create an alternating current. But I can't just push them unless I allow them to escape, to go back in here, and then I can keep pushing them through the wire.
charge. At the simplest level of description, that's what these four equations are telling us. It is best to think of this as a field, similar to the quantum fields of quantum.
No, it's best to think of this as things radiating. And how do they radiate? Just like how does the Earth radiate anything? Well, it radiates because it's reflecting the universe back at the universe. It's getting hit by stuff and then it's re-releasing that stuff again. After it goes through some processes inside of the Earth, and then it reaches its equilibrium of how much stirring you've done. And but it reaches a kind of equilibrium with the universe, and it just reflects back as much as comes in. It produces back out again, and that's how everything else is interacting. There's no whatever this crap is. You don't need any of that crap. All you need is this idea of there's energy, movement in the universe, and that objects can reflect it differently. They can absorb it and move. They can bounce it off and reflect it. They can do different things. And the fact that they do different things based on what's hitting them is why there is phenomenon like magnetism and electricity. But it's not made of this thing. You don't need to believe in this
quantum field theory that I spoke about in another video. But for visualization, you can think of this as being similar to the gravitational field.
Similar to the one you've made up that, again, is it's partially accurate, okay, but it's obviously not a three-dimensional model, so it fails right there, because, it's what are these fabrics going in all kinds of directions? I mean, it doesn't make any sense in 3 dimensions. It's incomprehensible in 3 dimensions. There's no way to understand how it could possibly work in 3 dimensions as that. And if you 3-dimensionalize it, what do you get with gravity? Oh, that's right. They will draw it. They will analyze it as if it was a fluid, as if it was a pressure equally imposed and converging on the center of the thing's mass. Okay, that's how they'll teach the subject of Einstein's bent space, is when they're teaching it in 3 dimensions, it just turns into a charge.
First equation is a formula that tells us how electrical charges create electrical fields. It's based on concepts that...
Right, so there's no electric field and magnetic field and all that crap. There's just the fact that electrons and protons do in fact radiate a different light, a subtly different light. The electron radiates a red light, you could say, and the proton radiates a blue light and reflects a blue light, and they have an opposite effect on each other. When the blue thing gets hit with the red thing, it does one thing, and when it gets hit with the blue, it does the opposite thing, the 2 interactions. So I've been over all that. But you don't need to go any further than this. This is the core function. Radiation. Period. Straight line force.
Developed by Carl Friedrich Gauss. It basically tells us that if you have an electrical charge, there will be an electrical field emanating from it. If you want to know the strength of this electrical field, you can calculate it using this equation. Note that the strength of this electrical...
all this, again, so the divergence of the electric field, right? You're just talking about this R² rule. The electric charge density, you're just charging what's the origin strength. And the constant is just a made-up thing, okay, because there's a lag, okay, between how fast these rays can get from point A to point B. So the further away you are, the more that lag is going to have an effect. It's going to take time for the force to interact with you, and so that's the only reason why that constant exists, is because this doesn't happen instantaneously. There's a little delay in how effective this charge moves. But that's it. There's nothing that is that complicated. No. If you were going to convert that equation into a mathematical diagram, it would just end up, like I said, all you would end up doing is saying, well, here, if I make 10 rays coming off this object, and I call that 100 watts, I'll know that out here I'm only going to get hit by, 0.7 ray, and therefore it's 0.7 of the amount of lumens are going to hit this surface.
Field is proportional to a constant called epsilon naught. This is known as the vacuum permittivity.
Yeah, so it's not known as that anymore. Okay, so this is part of the lie. These were made up constants. Okay, epsilon 0 and mu 0 or whatever it is, made up constants. They never were measured. They never went out and measured something called the vacuum permittivity. There was no experiment to measure it. These constants were created because they worked. That's it. They were the number that worked in terms of if you wanted to calculate something and it was speed dependent. That is, like you had a variable charge or you had some kind of thing that was where you knew you were transmitting a signal to the other thing. There was a speed dependence. And that's the only reason why the constant exists. And that's why it's in the bottom of the equation, is because it's not the speed of light. It's a derivative of the speed of light.
This is a property of the vacuum of space. It can be thought of as the resistance of free space.
Just to be clear, they have renamed them. So, I don't know if they did that 10 years ago or 15 years ago, but they now just call the two constants the electric constant and the magnetic constant. So they've changed their name because they know this was bullshit, because there is no such thing as this permittivity. It was never measured.
Against the formation of an electrical field. The second equation is referred to as Gauss's law for magnetism.
So this is kind of just bogus, okay? It doesn't mean anything. That, yes, obviously charges by themselves, an individual charge can't possibly be a magnet, okay? So they've taken this to say there's no such thing, okay, as magnetic monopoles. But all this equation is saying that is when you have an individual charge, okay, and it's not, the other, let's say the positive is here, but it's 17 light years away. Right? There's no evidence of a magnetic field here because this charge is so far away that there's no detectable mixing of the two forces. I mean, the mixing is so minute that it can be ignored. It's too tiny, the amount of mixing that you're getting. So it's without consequence, zero. All right? It's not based on any exact experiment, not based on anything. It's just saying that a single charge in space isn't a magnet, okay? It's not a dipole. There's not a pole here, right? There has to be a pole here to be magnetism, right? Magnetism has this different rule because the two forces will mix. When the single charge is somewhere, it's obviously not a mixed field, okay? It's not mixed. There's no dilution with any blue light, right? If it's a red light and there's no blue light, right? So it doesn't mean anything. It doesn't mean there's no such thing as magnetic and monopoles. It means that when you have a single charge, it's not a magnet. This is not a dipole. This is a monopole. Duh! I mean, that's how stupid this is. I mean, it's a trivial kind of bullshit. I mean, you're almost like, what? You've concluded there's no such thing as a magnetic monopole because a single charge isn't a dipole? Duh! An electron by itself is not a magnet. Yes. A proton by itself is not a magnet. But as soon as I put the two of them right next to each other, yes, I have a magnet.
Equivalent of the same equation for magnetism, but it's kind of a negative law. It basically says that if you have the same sphere, but instead of having a charge inside,
right. So it's the same charge inside. Instead, it was you put two poles inside of each other, which you can't do anyway. So that would theoretically be impossible. So you can't have a single object that has both polarity. Duh. But the point is you can have a dipole, and that's magnetism. Magnetism isn't positive being inside of a negative or a negative being inside of a positive. That's not magnetism.
a magnet.
I mean, it's almost as trivial as that, right? What they're basically saying is, look, if I put the attractive force, okay, so this one's attractive to negative, right? Okay, so this one's attractive to negative, and then I put the negative charge inside this, right? And so obviously, then this will be radiating exactly the same thing going out for an electron. It would be pushing it away. So it's going to push exactly the same amount as it's going to pull, and therefore would have a zero effect on anything next to it, right? Anything next to it would just say, who cares? That's irrelevant because it's pushing me and pulling me exactly the same amount. That's all that's saying. It's not saying that dipoles don't exist, magnetic, that they aren't a byproduct of exactly the same machine.
You'll never find a configuration where the magnetic lines of force always point outward or always point inward. There's always as much field pointed out as there is pointed in. It will be in loops. In other words,
it wouldn't be in loops. So again, no, it would be in exactly like the light bulb example, except you'd understand that the red and the blue have an inverse effect, so that if I actually did put their rays right next to each other, there would be nothing, because they have this opposite effect on things. Pull versus push.
magnet will always have two poles. There are no magnet.
So this is where they took something perfectly logical, that if I put the push device inside of the pull device, I'll end up with nothing, right? So if I put the two ends of the vacuum cleaner and I tie them together, yes, nothing's going to happen, It'll be just sucking the air it's blowing. It's not doing anything. I mean, the well and the mountain, I put the two of them inside each other, I get flat ground. That kind of idea. Duh! That has nothing to do with this. What they're going to say now is just stupid.
Magnetic monopoles. You cannot.
So he's saying there's no magnetic monopoles when we know atoms are become little magnets. And the reason why they become little magnets is because one end is positive and one end is negative. One end is electrons, one end is protons. We know that's what causes a thing to become a magnet, is arranging the charges. The charges create the magnet, the electrons and the protons.
Have a positive magnet or north pole by itself or a south pole by itself. You might say, well, I can take this magnet and cut out the north pole. Wouldn't that create a monopole? No, you would just create a smaller magnet.
Right, that's if you have 1 million atoms. Right, I have 1 million atoms, okay, and I have them all lined up as little magnets, right? They're all lined up as little magnets. They're all lined up as little magnets, okay? And yes, I cut the magnet in half. Yes, they're still all lined up north-south because they were all north-south, 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 going all the way through the magnet. So I cut it in half, and what I'll basically be doing is cutting it at a jagged line because that's how it's going to be set up. And so this end will be north, and this end will be south, and this end will be north, and this end will be south. So it's going to break and create that configuration, and this will be the north end, and this will be the south end, and blah, 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 blah. But what happens when I finally get to an atom? Well, then the north and the south are going to be obvious. The polarized atom is a magnet. So when I separate the electron from the proton, it'll be quite obvious I didn't create two new magnets. I created a positive charge and a negative charge. And if I want to make the smallest magnet you can make, I just take an electron and I take a proton and I put them close together and I made a magnet. I mean, this is so, it's just so stupid for them to say this. Oh, what happens if you cut it in half? What happens if you cut it in half? Well, what if you've cut them in half so much that now you're down to a single atom? If they just thought about that, well, what happens when it's a single atom? And I'm going to cut it in half. Well, I know the single atom, especially in things like iron, has a decidedly positive side and a decidedly negative side. When I pull them apart, it's going to be decidedly proton-electron.
With two poles. You can keep cutting this in half over and over, and you would always have two poles.
See? You would always have two poles. So you can keep cutting the magnet in half forever, and you never get to atoms. Never happens. You never get to an atom and cut the atom in half. Never happens. Shit. It's so stupid.
The third equation is called Faraday's law. This law basically says that if you move a magnet, you will create an electrical field. In other words, if you change...
Right, so if you introduce a field, it causes change. If you move the field, it causes change. Yes, and if you change atoms and crystals and metals and certain things, you'll get a reciprocal effect of either causing electricity, or you could cause another magnetic field and to be radiated back at you. You could push the electrons into a position where now they'll reflect more field back at you. And then you get into paramagnetism and different other effects you can have. But yes, you can have an effect on something by introducing a charge. Anytime you introduce a charge anywhere, you move it anywhere, it affects every single other electron within its proximity. Anything that can see it will be moved by it.
Change the magnetic field with time, it creates an electrical field. What does it mean to create an electrical field?
So there's no such thing as an electrical field or a magnetic field. There's just two forms of radiation. And it can either be the radiation that reflects off electrons or the radiation that reflects off of a proton.
It just means that you put a charge there, it will be affected. It will be accelerated. This equation tells engineers how to generate electricity from a generator.
All right, so again, this isn't what told engineers how to do anything. All of these generators were invented a piece at a time. That is, they figured out first, like I said, with telegraphy, they figured out how they could move a stick up and down with a magnetic field. And the first motors were that bad, right? They flipped it when it was a little bit off. They flipped it over here, and then they flipped it back, and then they flipped it back. But they didn't even have a round cylinder that they were moving the magnetic field through. And so it was terribly inefficient. That's the process. It wasn't an equation that solved the problem. It wasn't some equation that gave them the right answer.
You can take large magnets and rotate them, and if you put a wire near it, as you move the magnet, then electricity will be created in the wire. This is because there are electrical charges in the metal wire.
Right, and this is stuff Faraday figured out, okay? He figured out that one induces the other and the other can induce the other. So we already knew this, that electricity can cause a field that will cause magnets to move, and magnets can move and cause current to move in a wire. So that was what was established 100 years before they even had an inefficient motor. So it's not like there's some direct connection between, okay, we figured this part out, and they figured it out so mathematically precisely that it just instantly made a motor. No, people had to sit there and mess with it to get it to work. The engineers, frankly, didn't understand the theory all that well. And all they were doing was saying, hey, if I put two magnets, it works even better.
And as electric field lines are created, these charges will move, creating a current of electricity. The fourth equation is Ampere's law. It basically says that if you have a moving charge through a wire or an electrical current, you generate a magnetic field. In other words, two wires can be attracted to each other.
So they're both Faraday's law, frankly. I mean, it's the same concept, just in reverse, so no surprise.
If they have current flowing through it, the equation will tell you how strong the magnetic field would be.
Oh, the thing to understand here, though, is, see, they didn't really give you much of the details. This idea of just putting current through a wire won't help you much. So this is another one of the things where they had to figure out how to maximize the effect. And that's when they figured out that you had to what you really need to do is coil the wire. All right, now the straight wire will create a tiny bit of potential difference in terms of a magnetic field. A little bit of a magnetic field will be created, but it's incredibly weak. And it's not until you figure out this coiling idea that you can maximize it. And then you put a core inside the coil, and that becomes super magnetic. Something ferrous, something with iron in it. And then you really maximize the effect. But the effect is really what's happening inside the coil. The coil allows you to create a place where energy can be trapped. And that's what allows you to create this enhanced field, is that when you trap it and then force it inside of a piece of iron and you magnetize the iron will become a very strong magnetic field. But that's the only way you can take a coil of wire and get a magnetic field out of it, is by coiling it. If you don't coil it, if you just have a wire that's really long, you're not going to create any kind of magnetic field. It has to be coherent. It has to be, to maximize the magnetic effect, you have to get the coil to you have to get as much light shining on, so to speak, as much light as possible shining on the iron to cause the iron to become magnetic.
So if you have a given current flowing through a wire, let's say 1 amp, and you are 1 meter away, how strong would the magnetic field be at that point? This requires another constant of nature called mu naught. This is known as the permeability of free space.
So this is known as the magnetic, the electric constant, I guess. And the other one's the magnetic. Well, I guess this is the magnetic constant now. But that's all. So I'm just saying they're completely arbitrary. They never measured something called the permeability of space, of free space. That was never measured with some permeability detector.
Can be thought of as the ability of free space to allow magnetic lines of force to go through it. Note that there are two terms in this equation.
So again, allowing it to go through is another way of saying how fast it happens, right? So that's all this is about, is how fast, how long it takes the any effect in any change you make to the charge to affect the object, because it takes time for the energy, the rays, to get places. So if you move Saturn, it's gonna take 8 minutes or whatever it is for that movement in Saturn to be conveyed to us, where we would see, hey, Saturn moved. So that's all that's saying.
One term tells you that moving electrical charges can create magnetic fields, and the second term tells you that moving electrical fields can also create magnetic fields. This idea of magnetic fields being created from electrical fields was Maxwell's addition to Ampere's law.
Right, but it really wasn't, frankly. It's just a reshaping of the same argument. And what else do I need to... So again, but it's all this, all of it can be understood by just this ray map. The ray map will give you the right directions. So if you want to know how far a house is from some other house, I don't need these equations. All I have to do is draw the map and measure the distance. So if I just draw the electron and the proton, or the north side of the magnet and the south side of the magnet, as something radiating lines of force, I can see where the lines intersect. I can see where they're diluted. I can see where they're doing push and pull, and I can measure it. I don't need these equations at all. The equations are just a summarization of that a consequence. They're just telling, okay, so they're just giving you a way, again, of drawing a different line that's telling you the same thing. And the more elemental and the more fundamental one is the ray description of the reality.
And he just thought it up in his head. It was not based on any experiment. He figured that there should be some symmetry with Faraday's law.
So again, this he says. Again, these were conversations that we're already having. Faraday had them. Everybody was poised about how fast these forces move. They all speculated.
Because if moving magnets could create electric fields, then moving electrical fields should also create magnetic fields. Now I want you to take note of epsilon.
So the only difference is when you hear the word magnetic, it's a dipole. Okay, it means that there's two charges right next to each other, and the other ones are just charges separated. Electricity is separating charges, making red light and making blue light. magnetism is making some purple.
Naught and mu naught. Both of these constants have to be measured since they are inherent properties of nature. They are
All right, so he says they have to be measured. There's no measuring. They never measured them. They made them up. They made them up because they knew, just from cause and effect, they knew when they did the experiments there was a lag. They knew it was there. It didn't happen instantaneous. So the math worked better when they put the constant in. The math worked less well without the constant. That's why the constant exists. It wasn't because it was ever measured. It was just necessary to get the right answers.
not derived from anything. You might say at this point, well, you're just talking about electricity and magnets. What does this have to do with light? So here comes the most interesting part.
Yes, the only thing it has to do with light is that electrons and protons, okay, light affects electrons, and that affects the atoms. And so that's the connection. Light is one of those forces. Light, I would argue, is red, if we're going to make them red and blue or whatever. But light affects electrons. It also affects protons, but it's doing the more benign perpendicular thing. So, I don't want to get into the complexity of it, but light is the force. Light is those rays coming off, and you just put them at a frequency. So a charge just makes rays by itself, and they're not at a frequency. They're not pulsing. But you can create those rays and make them pulse. You can have an electron, say, spinning around. You could use a spinning argument, but I don't want to do that, really. But you could argue that if I spun an electron around a proton, that it would be essentially pulsing. When it's over here, it can't be seen through this, blocker. So there's no pink. And then the pink will turn on when it's on this side, the strongest. And then the pink is off, and then the pink is on, and then it's off. Now I've made a frequency. And that's all light is part of a frequency spectrum, of possible frequencies with which you can send the force. The rays. You can have the rays turn off and turn on a frequency.
Let's take what we've gleaned from Maxwell's equations and now put it to practical use. Put yourself in Maxwell's shoes at this point. You're working with equations and concepts that other people really don't know about much in the early 1860s, and you are staring at them for a long time, trying to see some...
Right, trying to wave them. Trying to, again, he was an etherist, he loved wave theories, and so that's all he did. He waved something that didn't need to be waved.
Patterns here, and you are mathematically trying to figure out what these equations are telling you. So now you think to yourself, maybe I'll do a thought experiment. What if I take an electric charge and put it on a pole outside my house, and I just move it up and down, up and down? What will this cause? Well, if you did that, then according to Ampere's law, if an electric field moves or changes with time, it would create a magnetic field perpendicular to that. And because of the changing movement of up and down that you're making with the charge,
So you're going to affect things. So if you put this is all by itself, perfectly comfortable. You put this in the universe, you're going to affect this. And then this thing being affected is going to affect that. And you're going to have yin and yang. That's all you're saying. I'm going to create two things that are arguing with each other, and they will argue constantly. Yes, that will happen. But it's not there's nothing mysterious about it.
magnetic field will also be changing with time. And according to Faraday's law, the moving magnetic field would create another new set of...
Right. So all he's saying is, look, this is sitting here. I put this in here. This causes this to move. It either moves closer or moves away, depending on whether it's the same charge or a different charge. Well, when this moves away, then the field around this is changing, and so now this has to move because it's not in the same field anymore. That's all. This isn't meaningful in any way, except that we already know that electrons hate each other and protons hate each other, and they inverse, opposites attract. That's it. That's all you need to keep creating some sort of balance. It'll always attempt to balance to the circumstance. So if I change anything, I change everything. That's all you're saying. If I change one thing, I've changed everything. Again, if I can just make something poof into this room, boom, it's here. everything changes in some subtle way because I put this in the room. Certain things get hit with more light, certain things get hit with less light. Fact. Gravity changes, everything changes.
Electrical fields. Now, since the same thing is happening to these new electric field lines, that is, they're changing over time, they would in turn create new magnetic fields. And the new moving magnetic field would create yet more electrical field lines. So this becomes...
So again, this is just nonsense because that's not going to happen in empty space. You know, if I put a charge on a stick and I move it, well, it's not going to mean anything unless I have other charges. So unless I'm doing it near ferrous material or some other thing, it's not going to change anything. It's just going to be too far away from everything else to have an effect. So even that thought experiment fails.
It's like an unstoppable positive feedback loop of electric fields creating magnetic fields, creating electrical fields, creating magnetic fields, and so on. Each is...
Yes, every cause has effects. Effects become new causes, period. Doesn't need to be understood any deeper than that. There's no way to stop a cause from vibrating forever. Any cause, if it's in association with any other system, affects the system. Anything I change, the change keeps going.
Produced by the movement of the other. You have just created a self-propagating wave. This is analogous to throwing a rock in a lake. It disturbs the water, so the water...
No analogy whatsoever. No evidence that the universe or space is any kind of lake with a bunch of atoms cohesively stuck to each other that has any similarities at all, and that it sends energy in all directions and does all of it. No evidence that any of that crap happens. It's analogous to the sun. It's analogous to a light bulb. Much better analogies. You don't see the light bulb waving.
Starts to
now,
oscillate, and it pulls...
clearly I can oscillate the voltage, and turn the rays on and off, on and off, on and off, and create what you might think of as waves of light. But again, we know they're really discrete rays. They're really individual soldiers. The soldiers aren't a medium. When one soldier dies, all the soldiers don't die. They're not connected in any way. They're individual soldiers doing individual things. And you're just seeing them as collectives, in groups, because they were all sent in waves. They were sent at a frequency, and therefore they look like a wave. But there's no wave property built into them. It just happens to be an incidental consequence of the way you produce the soldiers.
Its neighboring molecules up. So the first wave will pull its neighboring molecules up, which
So, a silly thing, right? You know that one wave of soldiers isn't pulling the other soldiers, and it certainly isn't throwing soldiers in front of it. It's not doing any of that crap. There's no medium here. There's just force moving through a void, period. There's just a ray of photons.
Oscillates more water, which moves more of the molecules from neighboring water. And this is the way a water wave propagates. So now you're Mr.
Well, again, so there's just no fair analogy here. There's no propagating because of inelasticity in the water kind of nonsense. It's just not a fact. Space is not a medium, period.
Maxwell, and are trying to figure out what kind of wave you've just created. This wave must be occurring in nature because electricity and magnetism exist. So you think about that, well, what would this wave look like? How fast is the wave moving? So you calculate using what you think this...
So again, look, they already know photons are discrete. They already know they're quantizable in terms of their clumps of energy. So why make this silly wave argument when you know they're soldiers? The evidence points to them being soldiers.
B could be by manipulating the equations that you have. You do this by using advanced multivariable calculus, which Maxwell...
We know that photons don't interact with photons. I shoot a laser and I shoot a laser. Somehow the waves don't do anything. This bullshit doesn't happen. Okay? There's no medium.
Was exceptionally good at. We won't go through how it's done here, but what Maxwell comes up with is 1 over v squared is equal to epsilon naught times mu naught. And solving for velocity, you get that it's equal to the square root of 1 over epsilon naught times mu naught. So what the equations are saying is the velocity of this wave is in...
What the experiments were saying was that there's a speed at which this effect of a charge or this effect of a magnet can affect something. It happens, there's a delay. And that's all. They already knew it from the experiments, and all Maxwell figured out was, well, yes, this is what you've discovered through experiments is, yes, exactly the function of this force that we call photons. It's doing the same thing. It's moving at the same speed.
Inversely proportional to the permittivity and permeability of free space. Does this even make sense? Well, permittivity...
It doesn't make sense because they're not derived. The constants were figured out as a necessity, not as something you measured. They exist to make the math work. They don't exist for any other reason. So you figured them out because you had to explain why the experimental results were what they were, and why your superficial understanding of what was happening wasn't correct because there was some reason that it wasn't as effective as you thought it would be, and that's why the constant exists. Constants are introduced to stabilize sometimes, and that's all they were. They were there to stabilize the equation, to make it right instead of wrong.
Can be thought of, as I said earlier, as the resistance of free space against the formation of an electrical field. Think of this like viscosity. A more viscous fluid like molasses.
So just more nonsense. It just has to do with speed. It just has to do with the fact that when you're going to change the atoms inside a wire, it's going to take a little longer, okay, than when you're just going to bounce force off a charge. So, that's it. This is just how much time it takes to move the change from one place to another, for the change to take effect.
Would be harder to swim through than water. You wouldn't swim very fast in molasses. Similarly, a wave flowing through a substance with lower permittivity would propagate faster. For free space, epsilon naught is equal to the following number. And permeability can be thought of as the resistance of a material against the formation of a magnetic field. And
so again, just more nonsense, because we know what it equals. It equals the speed of light, okay? So why play this game pretending that these two elements exist when you know the real element that exists is the speed of light, which is the speed of gravity, which is the speed of magnetism, which is the speed of electricity. It's the speed that these rays of force move at, period. There is no permutivity and permeability.
It's equal to this number. So it makes sense that the velocity of any wave would be inversely proportional to the resistance of the substance it's traveling in. You might at this point ask, well, why are mu naught and epsilon naught those exact values? That's a real good question. No one knows why.
Okay, so, yes, of course we know why. It's because it makes the equations work. Just like all of the observed data for gravitation back in Newton's day. If you took all the knowledge that they had, the fact is, if you do the equations accounting for the speed of light, that is, accounting for your observations being wrong, not explicitly correct because you're seeing the light 8 minutes too late or 15 minutes too late, and you make those corrections, the theory does better at predicting the orbits. So it's reason to believe. That's all, and that's how those were invented, through the same mechanism.
These are just the constants of nature. These are properties of free space that tell us how fast magnetic field...
They're really not a property. The only property is the speed of light. And because they have bisected something that's just one thing, charge is the only phenomenon. They've bisected, but by calling it, when they're dipoles, it's one kind of theory, and when they're monopoles, it's another kind of theory. So they bisected the speed of light into two things that add up to the speed of light. So that's all it is. There's nothing else happening here.
And electrical fields can interact with each other. If there's a finite speed at which the electrical and magnetic fields can interact with each other, then it sets a limit on how fast these fields can propagate through space. In a different substance or a different universe, these constants...
No, the fields don't propagate. You just move the charge, you move its field with it. Just if I move the Earth, I move its gravity with it. The charge moves with the charge, the charged field. There's nothing else. And the rays are just rays, and they move at the speed of light.
Could be different. Now we take the measured values of these two constants and do some simple math. Lo and behold, what you find is that the wave you've just created is moving at about 300,000 kilometers per second. This is really fast. This would go all the way around the Earth almost 8 times, or close to the distance of the moon in one.
It's the speed of light. It's the speed of all the forces. So it really should be just called what it is. Instead of the speed of light, it should just be called the speed of force, because it's the same speed for the charge radiation, is the same speed as the gravity, is the same speed as the magnet, is the same speed as the photon, which is really just turning the rays on and off. It's just blinking the light.
Second. What kind of wave moves this fast? You're Maxwell and you say to yourself, wait a minute. You remember that in 1728, English astronomer James Bradley had calculated what the speed of light is. It's about 297,000 kilometers per second.
Yeah, 100 years before Maxwell. So let's understand, they already knew this 100 years before Maxwell, that this speed was significant. So there's no big surprise in any of this crap. They're just making it sound like this is the key moment in time and space when this was discovered. There was nothing really discovered that wasn't already discernible, that one could speculate about. Again, Newton knew the speed of light, all right, and there was every reason for him to speculate about the speed of the force of gravity, but he just didn't get around to doing that.
And a huge eureka moment hits him that light must really just be a manifestation of electricity and magnetism. It is an electromagnetic wave. Can you imagine how Maxwell's insight...
It's just rays, on, off, on, off, on, off. That's all it is. Blinking the force.
...from this must have felt. There was a point in time when Maxwell was the only person in the world who realized this. Now, he could not prove it at the time, but about 20 years later, Heinrich Hertz proved experimentally.
All right, so yes, 7 years later, Hertz didn't prove anything. He just demonstrated that what they already kind of figured out. I mean, they already knew light came in colors, and they already knew there seemed to be this radiation that we couldn't see, ultraviolet, and this radiation we couldn't see, infrared. So this wasn't, again, a big mystery. And all Hertz did was demonstrate that, yes, there's a whole big spectrum. You know, there's radio, and there's all these other frequencies, and these much lower frequencies. And it just took them 7 years to figure out a way to see them. So that's the other thing to understand is we can't just see this force easily. We have to see it in some, we have to create a special circumstance that allows it to become visible. And we never see it directly. We see it by amplifying it through some device that is triggered. How do you even say that? And so obviously there could be other force here that we're not seeing, like gravity. Could be working the same way as these other forms of just radiation.
That Maxwell was absolutely right. And the rest of the story is that about 40 years later, another great scientist by the name of Albert Einstein did his own thought experiments inspired by Maxwell's equations. And
right, that make no sense at all, and he doubled the effect of gravity on just photons. So the only thing in the universe that's twice as affected by gravity is the special little photon. And again, the proofs were silly, and the proofs suck. They're weak evidence for any of this idea that there's anything called relativity in any other sense than, of course, two things that are moving the same can have relative differences. I can bounce this one up and down, okay? I can move them the same, and this one bounces up and down. Oh, they have a relative difference. So what? That doesn't mean one isn't both of them aren't really moving through real space. So, just bullshit.
Thought experiment was based on one simple assumption. He asked himself, if the speed of light is an inherent property of space, why would the speed be any different based...
No, that's not the argument. The argument is that somehow you change instantaneous because you change somehow when you see it. When you see it doesn't matter. Of course, if I'm between two objects that are going to bounce, and I'm closer to one and further from the other, and the distances are really large, therefore the speed of light becomes relevant, then of course I'm going to see one move before I see the other move because it's going to take light time to get to me. So what? That doesn't mean they changed the reality. That doesn't mean the physical reality at all wasn't that they jumped at exactly the same time.
in the speed of the observer. It shouldn't matter whether you measured the speed of light moving on a fast train or whether you measured it standing still. It should be the same regardless of your reference frame.
Well, again, that's going a step further and saying something I don't think even Einstein was saying. So Einstein was saying that the thing that's constant in the universe is the speed of light, that never changes. Obviously, your perception of it's going to change if you're moving very fast into it or moving very fast away from it. Okay, the fact is you'll get to your destination quicker. So the light isn't moving any faster, but you will move towards the photons. You're going to see them sooner. It's just a fact because you've changed the distance.
It was from this simple assumption that he came up with the special theory of relativity in 1905, which changed our ideas about the nature of time.
So again, changed your ideas because you bought the silly fable. I was never changed by the Three Bears story in any significant way because I never bought this idea that bears talked and smoked cigars and wore hats and went for walks and porridge and all that crap. Didn't fall for any of it. So frankly, I didn't get changed.
In his life, when people suggested to Einstein that he stood on the shoulders of Newton, he corrected them and said, "No, I stand on the shoulders of James Clerk Maxwell."
Right, who made fundamentally a wave guy, and who messed up something very simple, straight line force of charge, and decided that, oh yeah, well, I'll make the same mistake Faraday did, and I'll start bending reality. No need to bend it. You can keep the straight line model. The straight line map will give you the right answer. You don't need to bend anything.
The man who inspired not only Einstein, but to a large extent is responsible for creating the equations used by every electrical engineer to create some of the most cherished...
Alright, so again, just more bullshit, way overdone. They're simple little formulas. They don't create anything. The creation process is a whole different kind of trial and error story, and this theory doesn't give you the answers. They'll keep hyping this crap, and it's just that. It's crap. It took them 25 years to figure out how to make a blue LED. 25 years. Because the theory didn't help them any. It didn't provide the answer.
and useful technologies that we use today is James Clerk Maxwell. And as the history guy likes to say, this is history worth remembering. Guys, if you want to learn more about the...
Propaganda worth propagandizing about. So again, these people, they're terrible authorities. They don't even do their own research. Sucks. They're just telling us a fable and a fake story, like there was some real constants. There was never any permeability of space that was ever tested. It's just a nonsense. Again, well I've already done it. You can believe what you wish, but this story isn't the real story. Okay, it's crap as a story. So, till the next time and such.